So, plan for today is we will do today's lecture, take our break about 7:15, 7:20, somewhere in there, come back, finish the lecture. Hopefully we'll finish it somewhere around 8 o'clock. We'll stop whenever we finish it. We'll stop, we'll go over last week's homework as a sort of a review for the quiz. We'll take the quiz, ideally at around 8:30, so you have about 15 minutes. The class officially ends at 8:45. And then when you finish the quiz, you're done. So if you finish the quiz in 5 minutes, you go home. If you finish the quiz in half an hour, you go home in half an hour. I don't put a hard limit on the quiz time, as long as I don't think you're wasting both of our time. If you're sitting there staring at the ceiling, not working on your quiz, I'll save you your own time and tell you to turn it in. Okay? But I've never had to do that to anybody. Essentially, you have as much time as you want. Questions about anything before we start? Okay. So today's lecture is not going to have a ton to do with chemistry itself. It's about the things that we use in chemistry. Numbers in units. Okay? So, pretty much every numerical answer you're going to give me this semester has to have a unit. If I say, how much does this block weigh, you can't say 25. You have to say 25 grams, 25 pounds, 25 kilograms, 25 something. And you also have to be able to go between units. A great way to test whether you know how to go between units is to give you a problem where you have to have a number in the specific units, or certain units, in order to put it into an equation, but give it to you in a different unit. So you have to convert it before you can plug it into the equation. And this isn't a great reason why. This is getting kind of old. This is 99. But NASA sent an orbiter to Mars, and it didn't make it. It crashed because one team used metric while the other used inches and feet, and they didn't convert correctly between the two. And so this $125 million orbiter crashed. Units are important, okay? If you get it wrong, no, it's not going to cost yourself or the college $125 million, but it is going to cost you points, okay? So units matter. There are only 2 numerical answers the entire semester that don't require units, and I'll point those out. If it's not one of those 2 things, and you're giving me a number, please put units. So we use certain units in science, okay? Unfortunately for you, and unfortunately for me, when I started science, it is not the normal American units, okay? So for length, we use meter, mass is kilogram, volume is liter, time is seconds, temperature is kelvins, which possibly you've never even heard of before. And then looking several weeks ahead, if we're counting number of particles, that means nothing to you right now, but if we're counting the number of something that we have, we use the unit of moles. Okay? And so we can use not just meters for length, but derivatives of meters. So if I gave you something that was about that long, and I said, how long is that in some sort of a metric unit? What unit would you normally use, do you think?
Inches.
Looking for metric.
Centimeters.
Centimeters. But centimeters are essentially meters. And so what we can do is we take that base unit of meter and we add prefixes to it. And each prefix tells you what factor of 10 away from that base unit you are. So this line here is our meter line. Okay, there's an M down there for meter. Everything below that line is smaller than a meter. Everything larger than a meter is above that line. Okay? And so what we have here is the name of the prefix, centimeter, millimeter, kilometer, or kilometer. Those are prefixes you're familiar with. the letter that goes with that prefix, so a kilometer is a km, the m is from the meter, the k is from the prefix, centimeter, the cm, millimeter is mm. At the end here, we have however many meters each unit is. So a kilometer or a kilometer is 10 to the third meters. If you put 10 to the third into your calculator and hit equals or enter, it's going to tell you 1,000. So what this is telling us is that 1 kilometer is 1,000 meters. If you put centimeter 10 to the negative 2 equals in your calculator, it's going to give you 0.01. That is 100th. There are 100 centimeters in a meter. Millimeter is 10 to the negative third. That is 1/1000th, 0.001. My suggestion is when you get home, go through and add another column onto the end here. Just take these numbers, put them into your calculator, and write down whatever number it tells you. So this is 10 to the third, that's 1,000. 10 to the sixth is 1,000,000, that's 1,000,000,000. These are a little easier for you to imagine. If this is 1,000, 1 kilometer is 1,000 meters. That's not that hard to wrap your head around. But for centimeter, you get 0.01. 1 centimeter equals 0.01 meters. What does that mean?
100.
It's 100, yeah. And so if you're not comfortable with decimals, in order to go from 0.01 to something that you're comfortable with, take the inverse of it. Go 1 divided by that number, and that's going to give you 100. That's telling you that a centimeter is 1/100th of a meter. A millimeter is 1/1000th. There are 1,000 millimeters in a meter. A micrometer, that's 1/1,000,000th. There are 1,000,000 micrometers or micrometers in a meter. This is something you're going to have to play around with on your own so you get comfortable understanding what these prefixes mean. What does 100th of a meter really mean? What does 1,000th of a meter actually mean? So that you know if a centimeter is 100, that means there must be 100 of them in 1 meter. And these prefixes are the same prefixes that we use regardless of what measurement we are doing or whatever the base unit is. So this is length. Our base unit here is meters. The next slide is mass using the base unit of grams. And if I flip back and forth, the only thing that is changing is the m's are going to g's. The prefixes stay exactly the same. The numbers stay exactly the same. On the cheat sheet that you will have for every quiz and exam after today, there's a table similar to this. It will tell you these numbers. You just have to know how to use them, okay? You don't have to memorize these numbers, although some of them you will memorize without even trying. The ones we'll use very often are kilo, centi, and milli. Essentially, these down here, you won't run into all that often. There are on your cheat sheet, and so as long as you're comfortable using a table like this, you'll be okay. And we'll see examples of how to do a conversion like that. So gram, we said, was the unit for mass. Mass tells you how much matter that you have. Last week we said that matter is something that has mass and takes up space. Mass is the measurement of how much matter you have. It's very similar to weight, but there is a technical slight difference. Weight is dependent on gravity. Let's be optimistic and say I weigh 150 pounds. Okay? That is based on the gravity on Earth. If I go to the moon, there is less gravity. I'm going to weigh less than 150 pounds on the moon. If I go to Jupiter, there's much, much more gravity. And so I'm going to weigh more than 150 pounds on Jupiter. Because weight is dependent on gravity, in science, we need to take that variable out. We need something to be the same amount regardless of where it is, and that is mass. We use grams as our SI unit, but we also use kilograms. If you advance in science and you start dealing with more expensive chemicals, a lot of times you'll be dealing with very small amounts. Then you get down into milligrams, or a thousandth of a gram, or micrograms, a millionth of a gram. I even sometimes use nanograms, which is a billionth of a gram. So we measure mass on a balance, okay? And the name balance comes from the original way of measuring it, which was actually a balance, okay? But now we use the term balance for anything that measures mass. In lab, you will be using electronic balances. Technically, they are balances. I probably most likely will call them scales. If you call them a scale, that is fine. But technically, they are balances. So to give you an idea of how large these units are, one salt crystal is about 50 milligrams. So you can imagine how big 50 milligrams, or one salt crystal is. And so that is about 50 milligrams. That is 50 1,000ths of a gram. A gram is a nice tangible amount. A gram of water is about 20 drops. And so it's not a large amount, but it's a real world amount, right? When you start dealing with large amounts, then you have to go up to kilograms. Small amounts, you go down to units that are smaller, like milligrams. So, I said that a salt crystal is 50 milligrams. How many milligrams are in a gram? 1,000. If we go back to the table, 1 milligram is 10 to the negative third, which is 1/1000th. And so that means it takes 1,000 of them to build up to 1 gram. And so there are 1,000 milligrams in a gram. A person is about 70 kilograms. How many grams are in a kilogram? 1,000. Back at that table, it says kilo, the K is 10 to the third. That's 1,000. So there are 1,000 grams in a kilogram. How many kilograms are in a gram? 1/1000th. You can go either way. And so there are 1,000 grams in a kilogram, and so a kilogram is 1/1000th of a gram. If we go below the line, down to milligram, milligram is 1/1000th, and so there are 1,000 of them to get back up to the line. We also measure volume. Volume is how much space something takes up. Remember we said matter has mass and volume. So mass, we used grams. Volume is telling us how much space something takes up. You probably already know the equation for calculating the area of a box, a rectangular box. But to get the volume of a box, it's just length times width times height. And when you take length times width times height, it's very important that all three have the same unit. You can't take meters times centimeters times inches. They have to be all inches, all meters, all centimeters. And so you may have to do some conversions to get them all at the same unit. If we're talking about solids, we're talking about solid object, normally the unit that we're going to use are cubic centimeters. And so it's cubic centimeters because it was centimeters times centimeters times centimeters. And so normally for a solid, you would want all three dimensions to be in centimeters. This is cubic centimeters, centimeters cubed. It can also be abbreviated cc's. So when you're watching a TV show in the hospital and they say, I need 50 cc's stat, 50 cc's are just cubic centimeters. Because they are doctors, any pre-med people in here? Doctors make up their own rules. I don't know why, because they're doctors, okay? They're giving the patient liquids. We use cc's, cubic centimeters, for solids. Doctors decided they didn't want to follow the science rules, and so they use cc's. So here we have a box, okay? It says we want to know what is the volume of this cube. How can we find the volume of that cube? Length times width times height. We're not given length, width, and height though. We're only given one. This is the height. So how can we find the volume of that cube? Right. Because it's a cube, all the sides are the same. And so the length, the width, and the height are all 2. If this was anything other than a cube, if this side was just a little bit longer than the rest, you couldn't calculate it based on one number. But the fact that it's a cube means that they are all 2. So how would we find the volume of that cube?
2 times 2 times 2.
2 times 2 times 2. So volume, I'll abbreviate V, is 2 centimeters times 2 centimeters times 2 centimeters equals
8.
2 times 2 is 4 times 2 is 8.
8 centimeters cubed.
Centimeters cubed, yes. You have to have that unit. Okay? You have to have the unit, and you know it's centimeters cubed because that was centimeters, centimeters times centimeters, which is centimeters to the 3rd power. If you're dealing with a solid, most likely it's going to be cubic centimeters. You don't have to, at the end, think centimeters times centimeters times centimeters, so I need cubic centimeters. The way I look at it is I say, I want cubic centimeters, so that means these all have to be centimeters. If we're measuring the volume of a liquid, we normally use milliliters. Luckily, there's a very, very easy conversion between them. 1 milliliter is exactly equal to 1 cubic centimeter. 1 milliliter is a cc. So, if we have 1 milliliter, how many milliliters are in 1 liter? You remember what the milli prefix stood for? 1 1,000th. And so how many milliliters are in a liter? 1,000. What is larger, a liter or a milliliter? So we remember what did I say larger or smaller?
Larger.
Okay. I was thinking smaller, and I couldn't believe why everybody said liter. Okay. A liter is larger. Milliliters are small. Liters are large. This graduated cylinder, even though you don't have anything for scale, that is a 1 liter graduated cylinder, but it's marked in milliliters. 100, 200, 300, up to 1,000 milliliters. That 1,000 milliliters is 1 liter. A normal bottle of water is half a liter, which is 500 milliliters. Because half of 1,000 is 500. You know roughly how big a 2 liter is, right? And then there are smaller bottles, which usually are based on ounces, not liters. So let's convert 25 milliliters to liters. First of all, what is larger, A milliliter or a liter?
A liter.
A liter. A liter is larger. And so if we're going from milliliters to liters, do you think our number, our 25, after we convert it, is going to be larger or smaller than 25?
Smaller.
Smaller. The way I always suggest people remember it is larger units get smaller numbers. So because we're going from the small unit to the large number, the small unit to the large unit will have a smaller number. So our answer better be smaller than 25. Now, how many milliliters are in a liter?
1,000.
1,000. And so at the end of today's lecture, we're going to learn a systematic way to do conversions. But this one is simple enough that I don't think we need to use that system right now. We know that there's 1,000 milliliters in a liter. And we are starting with 25.0 milliliters. You're either going to have to multiply by 1,000 or divide by 1,000. It's all based on that chart that we started with. But referring to that chart gets a little tedious. So you can use and apply a little bit of logic here. We said that our number has to get smaller. And so am I going to multiply by 1,000 or divide by 1,000?
Divide.
Divide. If I multiply, I'm going to get 25,000. But if I divide, it's going to get much smaller. It actually comes out to be 0.025 liters. So what I did is I thought, does my number need to get larger or smaller? We said it needs to get smaller. The relationship between milliliters and liters has something to do with 1,000. And you don't even have to know which one is which. You know it's 1,000, you need to get smaller, so divide by 1,000. Multiplying is the opposite of what you want to accomplish. Here's another one. We need to convert our 25 milliliters to quarts. And we're given a conversion factor that 1 liter is equal to 1.057 quarts. Based on that conversion factor, what is larger, a liter or a quart?
Quart.
It's very tempting to say quart, but it's liter. This is a larger number than that, and so this must be a smaller unit than that. This says if Derek and I both have the same volume of liquid, and mine is in liters, and his is in quarts, he's going to have more of his quarts. A little bit more than 1 quart to equal my 1 liter. Units and numbers go in opposite directions. The thing that has the large unit gets the smaller number. And so we know the relationship between liters and quarts is 1.057. If I am going from 25 milliliters to quarts, do you expect my 25 to get larger or smaller?
Larger.
We're going from this unit to this unit. Is this unit larger or smaller than that unit?
Larger.
Smaller. So we're going to a smaller unit.
So we're getting a bigger number.
Our number has to go up. So we have two numbers. We have 25 and 1.057. We need to either multiply 25 by that number or divide it by that number. Which one is going to make our number get larger? Multiply. We take 25 times 1.057.
Wouldn't you convert it to liters first? Though? Yeah.
Thank you. Yes. I got to read my own questions. Okay. She pointed out, this is milliliters. This conversion is in liters. So we have 25 milliliters. We need to get it to liters first, which is what we did up here. And so we said 25 milliliters was 0.025 liters. That was the top part there. So now we can multiply it by 1.057. When you do that, you get 0.0264. That's 0.0264, and I have to put the unit quarts. Did my number go the right direction? Yes. That's a good way of checking your conversions. If the number went the right direction, assume you did everything correctly. If the number went the wrong direction, you know you did something wrong. Okay? So we're going to move on from conversions at this point. If you are completely lost, don't lose hope yet. Okay? At the end, we'll do another method for doing conversions. It's more straightforward, less logic. I call it conversions for dummies, not to mean that anyone who needs it is a dummy. I use it. So if I'm calling you a dummy, I'm also calling me a dummy. Okay? It will tell you exactly what to do. You can go from your starting point to your end point without even knowing why you're doing what you're doing. It will tell you exactly what to do, and what you get out at the end is correct. We're going to move on to density. We talked about mass and volume. Density is just the ratio between the mass and the volume. Meaning, if I have this much volume, how much mass am I going to have? For density of a liquid, we normally use grams per milliliter. That is, so many milliliters weighs X number of grams. For gases, we use grams per liter. Gases don't weigh very much, and so in order to get an amount that has a mass that we can actually weigh, we need liters. Solids, a lot of times, rather than using grams per milliliter, we'll use grams per cubic centimeter. And so essentially, whatever mass unit goes here will be divided by whatever volume unit you use. So if you use grams and milliliters, it'll be grams per milliliter. Grams in cubic centimeters will be grams per cubic centimeter. So looking at that graduated cylinder, there are a number of different liquids in there. They are separated based on their density. Which one is the most dense? The one at the bottom. How do you know? Probably the majority of you knew the one at the bottom was most dense. How did you know? Right.
It's heavier because denser things are more compact, so that means there's more mass within it.
Correct. And so the most dense is the one that is the heaviest. The heavy things sink to the bottom, right? They all have roughly the same volume. And so if this part is the same, the heavier it is, the larger the density. Our equation for density is D equals M over V. Density is mass divided by volume. If V is the same for all of them, our density is going to be determined by our M. A large M will give us a large density. So you know heavy things sink. In terms of density, higher density just means it is heavier. And so this is based on their density. The brown one at the bottom is the most dense. The one at the top that looks like vegetable oil is the least dense. Give you an idea of what some normal density numbers look like, we have some up here. And so helium and oxygen are gases at room temperature, and they are very, very, very low density. 0.001 grams per milliliter and 0.0001 grams per milliliter. It's almost an unmeasurable amount. That's why gases float. Because everything else in the room that's not a gas is going to be more dense, and so it sinks. That's why that desk is sitting on the ground. If the air was more dense than the desk would float up to the ceiling. But the solid desk is more dense than the gas. Liquids are generally in the 1 to 10 grams per milliliter range. Water, by definition, is exactly 1 gram per milliliter. And then solids are more dense. Looking at everything on there, all of these examples, is there one that you see that doesn't seem to make sense? Water and ice. When we talked about how the molecules looked how the molecules looked in solid, liquid, and gas, we said in gas they were far apart, liquid they were very close, and in solid they were essentially as close as they could possibly be. If you pack more atoms into a smaller space, the density is going to go up. And so normally, gases are the least dense, solids are the most dense. But water is 1, liquid water is 1, and ice is less than 1. Ice is less dense than water. How did you already know that?
Ice floats.
Ice floats. Let's go back to our cube. If we're told the mass of the cube is 11.2 grams, what is its density? So our density equation is up there. It's also up here. How do we find and calculate our cube's density?
11.2 divided by 8.
Right. So we've got 3 variables here, right? Well, if we're dealing with the equation, my suggestion is to always figure out what each variable is. So I have D, I have M, and I have V. Do I know the density to begin with? No. Density is what we're looking for, so we don't know what that is. Do I know my mass?
Yes.
Yes. It's directly given to us. It's 11.2. Do I know my value?
Yes.
Yes, but indirectly. We're told the size of the cube is 2. Earlier we calculated 2 times 2 times 2 was 8. And so our volume is 8 cubic centimeters. I can just plug these 2 numbers in and solve for density. So I have 11.2 grams divided by 8 cubic centimeters. And that comes out to be 1.4 grams per cubic centimeter. Because but the mass unit that I used with grams, I have grams. Cubic centimeters, cubic centimeters. If I had used milliliters here, it would be milliliters there. So we already did that. Here's a person in the Dead Sea. Anybody been to the Dead Sea?
But you float there, don't you?
Yes, you float there. He's floating. Why do you float in the Dead Sea?
All the salt.
All the salt. So the Dead Sea has a very, very high salt concentration. What does that do, though, that makes you float?
Makes the salt water more dense.
It makes the salt water more dense. You can think of you in the water as 2 things, just like 2 objects in the graduated cylinder. The one that is more dense goes to the bottom. We like to think as the thing that's floating as floating, but in reality, it's more like the thing on the bottom sank. And so the water is going to the bottom. The person is on top of the water. What else is in this picture, other than the water and the person?
Air.
Air. Where is the air in relation?
Upper.
On top. And so the water is the most dense. The person is less dense than the water, but more dense than the air. Okay. Why So nobody's been in the Dead Sea. Has anybody gone swimming in both freshwater and saltwater? Have you noticed a difference? Supposedly, it's easier to float in the ocean than in freshwater. I've never noticed it because unfortunately fat floats, and so I float no matter what water I'm in, okay? If you're more athletic than me, maybe you can tell the difference between it. But we have freshwater is the least dense, ocean water would be more dense, and then the Dead Sea is the most dense down at the bottom. So we're going to look at two cubes. And to me, the trickiest part about this is just simply looking at the cubes. To me, there's an optical illusion. These two cubes are the same size. Do you see them as the same size? How many people see them as the same size? How many see the gold one as being larger? How many see the aluminum as being larger? See, we have all three opinions. To me, the gold one looks larger than the aluminum. I don't know why, it's just an optical illusion. But we are going to work with the assumption that they are, in fact, the same size. So, if they are the same size, and this says the cube of gold has a greater mass than the aluminum one, which of the two cubes has the greater density?
Gold.
Why?
Because bigger mass equals bigger density.
Right. So we have gold and aluminum. In both cases, the volume is the same. And so what's going to determine the density is our m. Mathematically, because this is on top of our fraction, as that goes up, this goes up. As that goes down, that goes down. And so gold has a larger mass, and so it will have the larger density. If you were not able to follow that, if you had this question and you couldn't logically follow that, you can always make up numbers. And so if we say they both have the same volume, it doesn't matter what it is as long as it's the same. So let's say they both have a volume of 2 cubic centimeters. And then it says gold has a greater mass. Let's make up numbers. Let's say the gold is 3 grams and the aluminum is 2 grams. It follows the rules. I can just plug these in and see which one gives us the larger density. So gold density would be 3 divided by 2, and aluminum would be 2 divided by 2, 1.5, and 1 grams per cubic centimeter. You probably don't have to do that, but it is a test-taking strategy for problems going forward. If you can't, and you're not comfortable, you don't trust your own logic, make up numbers. If you make up numbers that follow the problem, it will tell you the answer. It may take a little more work, but you will get the right answer. So here again we have gold and aluminum. This time they are in fact different sizes. So this says, assume these two balls have the same mass. Which has the greater density?
Gold.
Make it the same.
Well, it would depend on the volume if the fractions would be equal to each other.
Right.
You don't have enough information. to
But
answer that
aluminum is
question.
taking up more space.
You have enough information to answer this. And so the only thing we need mass and volume, right? And we know the metals have the same mass. And so in this case, mass stays the same. And so mass isn't even going to factor in to our density. What we're looking at is the volume. If a sample has a larger volume, as volume goes up, what direction does density go? down. Because this is on the bottom of our fraction, they go in opposite directions as the density. As that number goes up, we're dividing by a larger and larger number. So our answer is going to get smaller. As our volume goes down, density will go up. And so the thing with the largest density will have the smallest volume. So what has the larger density, the gold or the aluminum? Gold. The gold will allow us to divide by a smaller number. If we divide by a smaller number, our answer is going to be larger. Here's another example of density. We have regular Coke and Diet Coke. Why is regular Coke more dense than Diet Coke? So regular Coke has corn syrup. What does that have to do with anything? That's the right answer.
Diet Coke has a sugar substitute. I don't know exactly what it's called.
It used to be aspartame. I don't know if it still is.
So the last is coming.
And so regular Coke has corn syrup. That's its sweetener. Diet Coke uses an artificial sweetener. But why does that make one float and one sink?
Because it weighed corn syrup would weigh more, right? And wouldn't that work?
Well, if you put a gram of corn syrup and a gram of artificial sweetener, though, they would both be the same. It is based on the fact that one is corn syrup and one is artificial sweetener. How many people use artificial sweetener in their coffee? How many people use sugar packet? How many people have used both sugar packets and artificial sweetener? What's the difference between them based on how much is in them?
One sweetens the other way faster.
Which packet has more in it? The sugar packet or the artificial sweetener packet? The sugar packet has a lot more in it. Artificial sweetener is much, much, much sweeter than sugar. And so you don't have to add very much. In order to taste, for it to taste like you added a whole bunch of sugar. That artificial sweetener packet that you have, that Sweet and Low, almost all of what's in there is filler. It's not even artificial sweetener. If they put just as much artificial sweetener in there as you needed, people would sue them because they thought they were getting nothing. They have to mix it with filler so that you can actually see something in there. And so for the regular Coke, you have to put a lot of corn syrup in there. And so you get a lot of mass, it makes it sink. Diet Coke is essentially water with a little tiny bit of artificial sweetener. If it's essentially water, why is it floating and not just kind of hovering in the middle here? Carbon dioxide. There's carbon dioxide in there. There is most likely a bubble right about there. So the bubble inside the can is above the water, and the liquid inside the can is below the water. So this is coming back to our ice. We said those density numbers for ice didn't make sense. When you go from a liquid to a solid, it should get more dense. Because we go from gas to liquid, we pack the same number of molecules into a smaller volume. Smaller volume means larger density. And then when we go from liquid to a solid, we have an even smaller volume yet. The density gets larger again. But there's no debating that ice floats. It's because water is special. Water, believe it or not, is actually one of the weirdest chemicals on Earth. It can do some really crazy things, and this isn't actually the craziest one. There'll be another wacky one later in the semester. So this is liquid water. You can see roughly how packed together the molecules are. When they freeze and they make solid ice, They don't get closer together though. They form what we call a crystal lattice. And the crystal lattice for ice has a lot of empty space in it. And so the water molecules actually have to come back apart a little bit in order to form this crystal lattice. And so all of this empty space leads to more volume, but no mass. And so as that volume goes up when it freezes, density goes down and your ice cube floats. Next we're going to talk about temperature. Temperature tells us how much heat is in something. It tells us how hot or cold something is, but it's always relative. Okay? Temperature is always relative to something else. If you say something is hot, it's assumed it's hot compared to room temperature. But you have to compare it to something. And believe it or not, we measure temperature with a thermometer. You already knew that. In science, we use two different units for temperature. We use Celsius, which you have at least heard of, and then kelvins, which you may not have. These are equations for converting between them, and also with Fahrenheit. You don't have to memorize those. Those are on the cheat sheet that you will have. You just have to be comfortable using them. And so Fahrenheit and Celsius are kind of some wacky equations. Celsius and Kelvin, the ones we will be using, are a more straightforward conversion. To get Kelvin from Celsius, you take Celsius plus 273.15. To go the other direction, you take Kelvin minus 273.15, gives you Celsius. Again, these equations are on your cheat sheet, but that 273.15, you're going to type it in your calculator so many times that you're going to memorize it even if you don't want to. So here are the three temperature scales. Let's take a look at how they fit in with real life and think about how they were made. The one that seems the most straightforward is Celsius. Look at the Celsius thermometer here and look at temperature that water boils, room temperature, and ice melting. You can see that there are some nice numbers there. Water freezes at 0 degrees and it boils at 100. Dr. Celsius, or whoever made the Celsius scale, said this is whatever temperature water freezes, I'm going to say that's 0. This is the temperature that water boils, I'm going to say that's 100. And then let's just break that difference up into 100 parts and continue it down below 0 and above 100. So that's how Celsius was set up. Kelvin looks kind of strange. Those are just weird numbers. So how was Kelvin set up? Yeah.
From absolute zero?
Absolute 0. Down here at the bottom, we have 0 Kelvin. That's called absolute 0. That is as cold as it is possible to reach. And so in actuality, Kelvin is probably the most straightforward unit, because you just start at 0, and as you get more heat, as you get warmer, you go up. There's no starting somewhere in the middle and calling it 0. But what that causes is that real world temperatures, you get large numbers. I mean, you don't want to look up on your phone how warm it is and see 298 Kelvin. That's just a weird number. We're not used to dealing with numbers that large on everyday things. We like smaller numbers. So over here in America, we use Fahrenheit. Look at those numbers. Can you make any sense out of those numbers? No, you cannot. There was a good meaning person with good intentions who set up Fahrenheit. I'm going to assume Dr. Fahrenheit. The problem was his thermometer was so long ago, his thermometer wasn't very good. What is body temperature? 98.6. What is a very clean, round, good number close to 98.6?
99.
100. He said, body temperature is 100. Let's go from there. But as time went on and thermometers got better, people realized the body's not 100 Fahrenheit, it's 98.6 Fahrenheit. And so now, not a single number makes sense with Fahrenheit. But it's what we have, and if the US tried to switch to Celsius, it would not be true. So probably we're stuck with Fahrenheit for the rest of our lives. You will never use Fahrenheit in this class, but you will most likely be given Fahrenheit in problems. And so you need to take your Fahrenheit and convert it into Celsius or Kelvin, depending on whichever problem or which equation you're using.
You did say we got that on the cheat sheet.
Yes.
correct?
So you don't need to know how to do it, you need to know how to use the equations.
Okay.
Okay. Good with measurements? Questions on measurements? Next thing we have is precision and accuracy. In the real world, outside of this classroom, outside of college, in high school, and academics, most people use precision and accuracy interchangeably. And from my observation, when they try to make the distinction between them, they get it backwards. The precision and accuracy are, in fact, different things. Precision is how repeatable your measurements are. If you take repeated measurements of the same thing and all of your measurements are close together, that means your measurements are precise. If you get a bunch of measurements and they are not together, that is not precise or imprecise. So I am roughly 6 foot tall. Okay? So if you take my measurement, my height, and you say I am 5'11", 6 foot, 6'1", 5'11", 6 foot, 5'11", all those measurements are pretty close together. That is a precise measurement. But to be precise, you do not have to be accurate. Accurate is how close your measurements are to the actual value. And if you have a set of measurements, it's the average of them. So if I measure my height, and I say I am 2 inches tall, 3 inches tall, 2 inches, 3 inches, 4 inches. They're still pretty close together. Those measurements are precise, but they are nowhere near the actual height. And so those measurements would be precise, but not accurate. But if I say that I am 5 foot tall, 6 foot tall, 7 foot tall, you have a range there of 5 foot to 7 foot. That's a big range, right? The difference between 5 foot tall and Shaq is big. Those are not precise numbers. But if you take the average of those numbers, 5, 6, and 7, the average is 6. And so those numbers, believe it or not, are accurate. It does not matter how wide the range is for accuracy. All that matters is where the average is. If the average is close to the actual value, it is accurate. So here is a dartboard or an archery target. If you look at those spots, would you call those spots precise?
No.
Precise is how close they are together. No. they're spread out, right? You got some here and here and all over the place. Those are not precise. That's easy to see. Where some people have a little bit harder time is figuring out whether that is accurate. Because remember, it's not where each individual point is, it's where the average is. Some people look at that and immediately see, well, kind of where the average is. Some people struggle with it a little bit more. It's depending on how visual you are. The way I look at it is, there are more dots to the left of the middle than there are to the right. Does everybody see that? There are roughly the same number on the top as there are on the bottom. And so I would say the average is roughly in the middle this way, go up and down, but it's this side. So I would say the average is probably about there. That is not in the middle. And so that is not accurate either. This is not precise because they're spread out, and it is not accurate because the average is not on the bullseye. Here's another one. Is it precise?
Yes.
Yes. There's a very good grouping. They're all very close together. It's a clump. That is precision. These are precise. Are they accurate?
No.
No. Obviously, the average is somewhere right in here. It's nowhere near the middle. That is not accurate, but it is precise. What about that one?
It's precise and accurate.
It's both. They're close together, it's precise, and they're all in the bullseye, so the average must be right in the middle, and so it is also accurate. How about that one?
Accurate but not precise.
Accurate, but not precise. Precision is always the easier one visually. They're not together very well. They're spread out too much to be considered precise. But the average is pretty much in the middle. They're pretty well spread around equally the center. So it's accurate, but not precise. Okay, let's do some more conversions. Don't want you to forget. We need to go from 12 grams to milligrams. So first, what is larger, a gram or a milligram?
A gram.
A gram is larger. And so is our answer going to be larger or smaller than 12?
Larger.
Larger. We're going to the smaller unit, and so our number will get larger. Smaller unit means a larger number. So number one, we know we want our answer to go up. It should be larger than 12 when we finish. What is the relationship between a gram and a milligram? 1,000. So we know that we have 12.0 grams, and we know the relationship between them has something to do with 1,000. Are there 1,000 milligrams in a gram, or are there 1,000 grams in a milligram? 1,000 milligrams in a gram, correct. Let's say you didn't know that. We know we want our number to go up. We've got that number and that number. Do we want to multiply by that number or divide by that number? Multiply. If we multiply times 1,000, we get 12,000 milligrams. If you divide by 1,000, you're going to get smaller. So you immediately know it's wrong because it didn't go up like you were expecting. Now let's take our 12 grams and go to ounces. Again, this is one that's not metric, but the conversion factor is given to you. Based on that conversion factor, what is larger, an ounce or a gram? An ounce. How do you know?
It's a small number.
Has a smaller number. Ounce has a smaller number, and so it must be the larger unit. So we're going to go from grams to ounces. Do you expect our answer to go up or down? Down. We're going to a larger unit, grams to